Yeah. So this where they want you to show that it's equivalent. Yeah, yeah. So it's actually not that much work.
That's what we thought, and we were just confused as to what are they asking.
I think they just want you to. So you have something. I'll write. I assume you have this part where in the loop you have something like x is x plus v delta t, right? I'm not. There's indices.
Yeah, we have that, yeah.
And then you have also, so you have y is da da, right? Same thing. And then you have v x. I'll just write vx is vx plus a x t, or I'll even write. Sorry. Fx over.
Okay, this is what we did for
Do you want me to pull up two for context for you?
Oh.
is that
No, yeah, this is probably better than what they wanted.
oh
Okay.
Because I would say, yeah, this is very mathematical. Which,
That's what
again,
it's right?
well, I think what they want you to do,
that's for 2. And so we didn't know how to change that.
For 3.
this is actually probably,
Yeah, there's two for context.
yeah. And then, is this, this looks good. Were you wondering, so this looks correct.
Yeah,
For
so,
number
I
2.
think.
so we're trying to figure out how to
Well,
get it.
But you have at the bottom, this is something with t squared, right?
Yes, so that's like for the position. So for 2,
Yeah.
the axis define both the position and the velocity components.
Yes.
And so we did that.
Yes. Right, but then when they want you to show that they're, oh, I see. You're just saying show they're equivalent.
Yes, to number
Oh, okay.
3.
I believe,
Because they said we have to replace something with the average velocity.
yeah, so, okay. So
That's where we got stuck.
what they want you to do is easier, I think, than what you've done. So you're probably correct,
Oh,
but not,
good.
you don't necessarily have to, I mean, if you submit that, I'm sure it's fine. But, so, once we have this, so, okay, this is the original way to do it, where you have Vx times delta t, right? And Vx is this over m times delta t, right? So this, and then Vy, whatever. I'm trying to get in, whatever. Okay, and you have Vy, the same thing. So now this is obviously, I just replaced this. It's, you could put another a if you want the same thing. But these two steps are the first way they want you to do it, where you use the initial. So this step here is used, it depends actually, if you put this after, it's going to use the final velocity. But, so this is obviously, this is obviously the initial velocity in this loop, and this is the final velocity of the loop, right? So, and if you do this loop, like with this way, it's going to use the initial velocity here, and it's going to do what they say in 3, they say use the initial velocity. If you want to use the average velocity, all we have to do is replace, well, then we're going to need to talk about the indices. So obviously you put these in brackets or whatever you do. But so you get that, and then we would really replace, we actually have to do now, we have to put x after. So I'm going to erase these because we actually need to put the position after because we already had these computed. Well, actually, well, anyway, maybe it doesn't really matter. But xi plus 1 is xi plus vxi plus 1 plus vxi over 2. That's the average velocity times delta t. And now they just want you to take vxi plus 1. Now this is going to compute and it's going to be fine. But if you actually plug this in arithmetically, you're going to get xi plus 1, which is delta. So delta r is this, right? It's delta x, really. This is going to be this thing, right? Which is vxi plus 1, which is actually vxi plus, I'm just going to write this as ax. I don't want to write too many symbols, but ax times delta t. Okay, so this is, right, plus vxi. It looks really messy, but, and then times delta t all over 2, okay? And now we get what? Well, if we just expand this out, this is, yeah, this is going to be v 2 vxi delta t, but that we divide by 2, so we get that. And then plus, hopefully this is, yeah. So this is the initial velocity, v naught,
AT squared, there you go.
plus exactly, plus ax delta t squared over 2. Right?
Okay.
So this is delta r. Well, sorry, this is delta x, and then delta y is exactly the same.
Okay.
So this statement here is just saying that if you take this and you replace, normally we just have that the next step is given by, this is called the Euler method. I told some people about this, right? That phrase, Euler method. The Euler method just says that we only do linear things. Okay, linear meaning linear in our step time. So if we only do linear things, now of course you might think, well, it's not really linear because we're not going to get lines, right? But each step is actually going to be a line. That's the key thing. So when you do this simulation, you actually get that each step is actually a line. Now that's not true, of course. When you really do a real parabola, you can zoom in infinitely far and it'll not quite be a line. But with Euler's method, we always simulate them with lines, and we could take this. It's just the integral thing we do for integrals. But the point is that using these two equations, we have two things that are linear. We have the velocity and the position are both linear. But if we use this average velocity method, I mean, it should actually be equivalent anyway. Anyway, okay, what doesn't matter. I'm a little bothered by this now, actually. It should be equivalent in both cases. It should be equivalent even when we use the initial. But anyway, okay, let me, don't worry about it. The thing they want you to show in this problem is that using this average velocity, we can just literally plug in. And we actually get something that has a t squared in it, delta t squared in it. And that's actually, oh, here, okay. Hopefully we have enough chairs, yeah. Yeah, so this has a delta t squared in it. And so we'd actually use something that was linear, but we're actually going to get essentially
Parabolic.
kind of a parabolic, like,
Okay.
I mean, yeah, so I guess we won't even get straight, yeah, we won't get straight lines if we use the average velocity, I believe. That seems weird though. It seems like we should get straight lines. Anyway, this is all philosophy, but the point is that mathematically, they just want you to plug in, right? And now, if you do some actual integrals, you literally you can actually derive that, which you probably did, which is better than this. This is actually, because technically, if you wanted to derive it sort of exactly like how you derive this equation at all, the x is 1/2 at squared plus vit. This from kinematic, just from math, not from steps, is you take this and you do the limit. It's like the calculus limit you do, where you take like integrals to be the width of the rectangles is delta t, and you take those to 0 and you get an exact thing. So what you've written is probably more than enough.
So
But yeah,
how do we do? So with what I've written, how do I get? I should just compare it to this equation.
yes.
Or I should just do. I will do it linearly, so I can just do another side linearly, just as you did.
Yes.
Okay.
I mean, really, you could just write basically this, and this is what I thought the question was asking. Perhaps some people are going to interpret it more mathematically, which. No, I'm just going to assume that if you have this at least, that's sufficient.
Okay.
If you have more, that's even better.
Okay.
But you won't be wrong if you don't. But this is essentially what the minimum.
Okay, so I think we're on the right track.
I think so. Yeah, I'm gonna take a picture of this.
Go ahead, yeah.
Do you know?
Yes.
Like it?
No.
I think that answers the question.
Okay. Yeah. So. Okay. So. I'm thinking about something, but it's not about any. It's not that anything I said is wrong. I'm thinking about the fact that it seems like the initial, if you use the average velocity. Oh, okay. I see. So the difference between using the initial velocity and using the average velocity is actually not really that significant. This is what I was thinking about. It's kind of like saying, how am I going to make my lines? I'm going to take the velocity. I mean, I'm going to take the velocity here and boost up, or am I going to take the velocity that it would be in the middle?
Your approximation just gets closer or something.
Exactly. It should be identical, but we sort of shift one of the things over. So the fact that we get a t squared here doesn't tell us that. This is what I was getting at. What they're saying is a little bit not quite right. It's not that if we do the average velocity, we get a t squared thing, and when we don't, we get a linear thing. We get a t squared in both cases. It's just harder to see because we can't just plug in the equations we have. We actually have to do an integral. If we did the integral, we would actually see that that's always true because technically the acceleration is the derivative. It's like the derivative of the velocity, right? It's I plus 1 minus I. Actually, anyway, whatever. You see what the point is that it's actually like this always, and we know that's the case because, well, actually, we know it's the case because we get a parabola.
Yeah.
Because one of the, although it's over distance, but still, we get some kind of parabola. We know that there must be a t squared somewhere, and you can't see it unless you write out the average velocity. Then you can actually see it explicitly, but it's actually there all the time. So when they say that show that's equivalent, so that this is equivalent. Yeah, I guess they're right because they were saying like when you use the average velocity, when you rewrite it like that, show that it's equivalent, and you know that using the average velocity isn't actually mathematically changing anything. It's just shifting where you sample your velocities from for each boost. But everything should be identical. But of course now we can plug in things and see it a little easier that it has an actual explicit t squared in it. So the point is that it should be there always, and we can actually get this kinematics formula from these two linear formulas, and that's sort of, you never do this, so this is correct. You would never go to something less correct and more computable in a physics class, but that's why physicists don't really do things. But anyway, so this is how you'd actually break it. In other words, this is a step where you're breaking something down to finite segments and you're actually making it linear, whereas originally it was nonlinear. Anyway, does that make sense?
I think we were just confused as to what it was asking.
Yes,
Because
that happens a lot. Yeah, yeah. There's a lot of pages here. Oh yeah, they say there's method right there. Yeah. Okay.
That was our question.
So is this? Do you have any questions, Allison, from part 1? Before the questions 1, 2, 3, basically.
No.
What are we
We're
going
at
to?
7 or 8.
Okay.
Yeah, so we still got
We're at 8.
yeah, we're at 8 now.
So
So
now
we still
Yeah.
got work to do.
Oh yeah. This is the one. Who was I was talking to someone about this. Was I talking to you about this?
Yeah, Bob was very
Yeah, about how this is the thing about how small your times have to be to get an answer that converges. That's sort of a non. That's not a good. That's not. You shouldn't say that. They shouldn't say that. What they mean when they say to get an answer, not that anyone asked, but I'll just tell you. To get an answer that converges just means is it close? There is no actual. I mean, technically, it converges if delta t is less than 1. Right, because if it's greater than 1, this is going to explode. Right, so, because then, well, it won't necessarily explode, but if tilde t is greater than 1, we can't assume that this is small. So we can't really use the linear approximation, right? The linear approximation it's a Taylor expansion. These are all basically Taylor expansions, right? These are not Taylor expansions, but the fact that we broke it down to linear and the Euler's method works only when the parameter is less than 1. This does not have correct units, but pretend this has some units that are, I don't want to say seconds, but just, actually I'll say seconds. But if this is greater than 1, that means t squared is greater than delta t. Again, the units don't make sense on this. But this statement, if something squared is greater than that number, we can't do any small approximations at all. That's the whole point of the Taylor series, is that it's getting smaller and smaller, so we can cut it off at some point. So Taylor's theory is always right, in some sense, but we can't always cut them off and get anything useful if they sort of blow up. So the point for this is that when they say, and of course as t goes to 0, we get a closer and closer approximation. Now, of course, at some point, at some point, you'll get a slightly better approximation for the average one than if we do for the initial one. And so, but for some value of t, it'll be so close that it'll be the same. So I think they just want you to test both of them and just show that if you just try delta t equals like 0.01 and just try this method, right? So this loop and then the loop without this and without the 2, right? Which is the initial velocity. Just look at the end x and y. Well, the y position 0, but the end x position. And if it's, you know, if it's significantly, if it's 0.1 meters different than the other way, right? If this method and then the one without the average velocity has a range that's 0.1 different, that's kind of significant, I guess. And if it's 0.01 different, I guess that's pretty good. So that means it converges. So when they say converges, that's a math word that they shouldn't be using there. What it means is that it converges for this condition. But what they mean is, I guess, when it's close. So essentially when your actual linear approximation, not your sneaky delta t squared thing, but when you're this, you know, well, the actual linear approximation looks like that. Yeah, when you use that, what do you get basically equivalent to something where you have a slightly better approximation? At some point you will, if you have small delta t's. And then plot it, yeah. Yes. So then you want to plot 3 on the same graph with different drag coefficients. So hopefully if you have the your force here and x, and then of course you have everything with y, and if you have those appropriately computed, right? And they have to be within the loop, remember. The forces are not constant. You can't just compute the drag force and put it outside your loop. It actually has to be updated because it depends on the velocity, which is given right here, right? Then you should be able to get, if you, actually, what would be even better is if you, instead of computing f of x, you actually wrote out all the terms, which would be like, what is it, like c rho a, is this right? B squared, something like that. So if you wrote out all the terms, and then this is f. Of course, we want the actual x component, so we have to put like a cosine, or we could even do. I was telling a few people you can do this. V times Vx is the same as V squared cosine theta, which is the component. It's just like a shortcut computationally. It doesn't mathematically. It's not like a different thing. It's identical, but it's just because you already have Vx here, and V, of course, V is the square root, you know. Right, and this also you need to have in the loop is V, and so you also need to have this in the loop because it updates every time too. The net velocity changes. Anyway, so once you have this, now hopefully C is a parameter, and C and rho and A, you should set before the loop because they don't change, of course, and that way you can plot it. I was trying to think if you could do it all in one step. You'd probably have to do it in 3 separate runs of this thing with different values and plus, and I'll plot them the same thing. I don't think you couldn't do them all the same. You'd need to make up a whole bunch of new variables probably. But anyway, that's a MATLAB problem you can figure out. But hopefully then you can just set C equals something else, 0. And now if you set C equals 0 and you get like a completely different result and not a symmetric parabola, you've done something wrong. And so I would just make sure that when you set C equals 0, it goes like this, and when you set C non-zero, you know, maybe it'll do something drastic, but it shouldn't like go like that.
Should
or
follow
you know,
the trend.
It should do what you'd expect. Like it's like the water bottle problem from the last homework. Like that's actually kind of a good warm up for this because you want to see the paths and kind of you have some intuition of what's going to happen. It's not going to be symmetric anymore when you add air resistance in both dimensions because it's going to lose some x velocity at the top, for example. So even if you just look at the top, it's going to have just x velocity, so it's going to lose some x velocity, and therefore the second half is actually going to cover a shorter distance than the first half. So just forget about y drag and all that stuff. Just with x, even if it only had x drag, we would actually know that it would be sort of asymmetric. So anyway, that's just things to think about when you're looking to make sure your answer's right. But is that
Yeah, I think it's good for us. So we still got some work to do on that. So
sounds like fun.
yeah.
And I'll just say, so anyway, I'll be here. If you want to do, I talked all about torque. So if you saw I posted the video. Does everyone have access to the video? Mm-hmm. So I talked all about torque, and I tried to like go over it as if there was no discussion of torque in the class, which there wasn't really. And I went through basically not all the problems, but essentially all the problems. So I could do some of those again, or I could do there. I actually didn't do the last problem.
I was gonna ask you about that because
Yeah.
you said you were gonna try to get a better understanding for it. 'Cause
Sure. Yes. So that one I actually set. So I can do. Do you want me to do that, or does anyone object?
I'm here for whatever.
By all means,
All right.
please.
Sure.
I need all the help I can get.
Um,
I was not here.
So yeah. No. Well, even if you were here, it would.
Yeah,
I don't
I
think it
know.
would have.
I didn't even ask for notes. I was like, I'm just gonna watch his video. And
Yeah.
I can figure it out.
I mean, yeah. So this is probably one of the, I was telling other people, one of the hardest things in physics. I think is rotation. When you see rotational motion for the first time. And so yeah. Oh, so that one. So okay. What I said before about that one. I said you need like the moment of inertia tensor.
Yep.
You actually don't.
Oh.
Which means I could have done it the other day. I just didn't realize. The moment of inertia tensor is kind of complicated.
Okay.
Let me just tell you what it is. It's in the book. This is why I'm telling you. I've never in my life used it, and I don't think it's in any of the problems. So I highly doubt you'll need it, but I'll just tell you what it is so you know.
Anything?
Because you can have it on this.
So the moment of inertia as just a scalar is this. It's a number, right? Well, yeah, it's a number. There's a thing called the moment of inertia tensor, which is a tensor. In this case, it's a matrix. It has two indices, ij. I'll write the real form. Actually, yeah, let me write the real form first. It's dm xi xj. So this is the actual form. Now, this is because there's two indices here. So whenever I have a thing with indices that are not contracted, you know what contracted means? Heard that before? Oh, I guess they don't. Maybe they don't say this. Same language. Contracted means like if you have this means x squared. Because it's this, well, I should really write this. This means x1 times x1 plus x. This is like the dot product of x and x, right? Anyway, sorry. I'm getting off topic. The point is that there's two indices here. That means we have 9 possibilities for this, right? And we can put them in a matrix. And so this, if I is, this ixx would be like the first entry. So this would be like x dm x squared. This one here would be dm, and then it would be xy, I guess, and this would be dm xd. This would be dm y squared, yx, right? yz, and then it would be that, and this would be z squared, right? I didn't want these are the z, and I don't want to write them, but anyway. So this is the actual moment of a tensor. Okay, a tensor. I'll just tell you. He said something about a tensor that didn't make any sense. A tensor is an object with indices, coordinate indices, that transforms like a vector is an example of a tensor. So a tensor would be something like a vector sits, let's say the y vector, the y unit vector. Okay, that means that if you change your coordinates, right, then your vector would change correspondingly. It's kind of like that. Don't worry about the actual explicit transformation, but what it means is that if I have, let's say, a vector like vector A, I don't know why I'm putting it in parentheses, a vector A and a vector B, and I take my coordinate system and transform it, A and B will have new coordinates, but it's not like they'll be random new coordinates. They'll be systematic changes in exactly the way I change my coordinates. So if I call x y and I call y negative x, I can't actually call this plus x because then it's like the right-hand rule. I'd be messing up the right-hand rule. Anyway, okay. If I do this is called a rotation. So this is I'm taking the y, so this is y hat and this is x hat. This transformation here is a rotation 90 degrees because I'm taking the y vectors and changing them to negative x, which is that way. And I'm taking the x vectors and changing them to the y, which is this way, right? So this is a rotation of 90 degrees, okay? It has a matrix not like this, but a matrix corresponding to it, which I don't remember how to write, so I'm not going to write it. But it's a 2 by 2 matrix. Actually, I could write it. It's a 2 by 2 matrix and this column would be where the x vector goes, which would be 0, 1, and this would be where the y vector goes, which would be minus 1, 0. So this is a rotation by 90 degrees. This is a matrix. So if you take a vector, let's say my x hat vector, which is 1, 0, and I say where it would go, I'm doing matrix multiplication here, and I get 0, 1, and this is the y vector, which is this, so that means it rotates this way. Anyway, I'm going very fast here because you don't actually need to do this for anything. But the point is that these vectors are tensors because they transform just according to my coordinate transformations. In other words, all the coordinates, when I do this rotation, get transformed like this, and so do the vectors. Okay, so a tensor is something that has, a vector is a tensor with just one index, okay, because I only had to tell you the components along the basis vectors, basically. But if it has two indices, that means I have two coordinate dependencies, but they both separately transform just like that. Okay, now don't worry about, you don't actually have to do any transformations like this. It just means that, like, it's not like when you transform coordinates, you get some random new numbers. You get something that's systematic. In other words, the dot product is, another way to say it is the dot product between these vectors will be maintained even if I do this. Okay, okay, yeah. Okay, that's sort of not always true, but in this case it is because it's a rotation. But so the point is that if I have that's what a tensor is. When they tell you what tensor, that's what a tensor is. It just means it has some indices such that if I do some coordinate transformation on one of the indices, everything responds just like I did some kind of coordinate transformation on the actual coordinates. So tensors transform like the coordinates. Yeah.
So this will apply to rotations, transformations,
This should apply to all,
transpose.
not transpose. That's not a,
Sorry, I mean translate, not transpose.
oh, translate. Yeah. Okay. Yes. Translations. Yes. So translations are, yeah, that's a better example than the rotations. The translations are kind of obvious. It just means that, well, if I want to relabel my x equals 0 point to be here or whatever, yeah. If I want to relabel my x equals 0 point, I'm just taking all the x coordinates and adding, 5 to them or whatever, right? And that means that if I have a tensor that depends on x, I would just add 5 right in here and everything would be fine. That basically, you'll never see something that's not a tensor because it doesn't make any sense then. A scalar number, is also an example of a tensor. It's kind of trivial because it doesn't have any indices. So a dot product, for example, is just a number, and it doesn't have any indices. That means if I change coordinates, it doesn't change. So those are invariants, sometimes they're called. So anyway, everything we've been seeing with indices or anything like that, or vectors or matrices and stuff, basically are all tensors. So that's what he means by that. I guess I didn't really do a better job than him. But the point is that this is a tensor, but we really only need, for this problem, actually, I'm going to erase this now. But for this problem, we actually only need, it was like, there was like a rod. I guess I'll draw like it was like a rod and then like a chain, right, with some tension. And then I guess there was like a force here or something. And what did you have to find? I don't remember the.
Well, first is the free body diagram.
Oh. Yeah, so I'll erase this now. But anyway, this is the definition. It's in the book too, but you probably won't have to use it. I thought you had to use it for this problem. That's why I didn't want to get all into it, but I don't think you actually do. So we know that I for this, it's a rod rotating around its end. So if we'll just write this in case we need it. It's like 1/3 ml squared, right? For the length is L. And yeah. And so now we want to draw the free body diagram. So we have, actually, let's draw, yeah. So the free body diagram for the rod, well, of course, in the center, there's gravity, right? So now we're just showing all the forces. We're not worrying about torques right now. In the center, we have mg, right? At the end, we have some tension. Now, I don't actually know what direction it is. Okay, so yeah. Okay. Okay, and then at this point, I guess we have a force going somewhere else. We actually don't even know about that either. Right, so it looks kind of like this, right? There's no, I think that's it, right? There's just gravity. There's some tension going in some direction. So this is, when I draw this, this is not actually on a plane. Like, these are not, it's not flat. We don't know that for sure because we don't know that this makes like a triangle. It could make like a sort of weird shape, you know? Like, in other words, this point is not above this point on the same XY plane kind of thing. But it doesn't really matter. So the point is that there's two, that most of these problems we've been doing, we have like, two dimensions and we're breaking it into a vertical and horizontal forces. This time we have 3 dimensions. So this statement, this is the immediately thing we do when we draw a free body diagram usually, is we'd write like this, right? So this is what we've been doing. We don't usually have a z, but we've been doing this for a while. We said, you know, oh well, if something's just moving on a plane, like sliding, we know that the net vertical forces must cancel. That's just this statement being 0. And we know that the horizontal forces must be, maybe it's non-zero or something. Yeah.
Z in this case is just for the rotation plane, right? No movement of the z-axis.
Z, I just mean literally this is
Okay. Yeah.
X, Y, Z. Yeah, this is like I'm using the basis that they're giving because they'll tell you what the vectors are. But I actually know that it's not accelerating in any of these dimensions, right? It's supposed to be stationary, so these are all 0. So I know the sum of the forces in the X, some forces in the Y, some forces in the Z have to be 0. So I can now actually label these forces. So I'll say force of gravity. Now this is the point where normally we sort of don't explicitly write out the vectors because we don't really need to because it's sort of, but they're really there. So f of g is what does it look like in a vector form? In a vectors I'm going to write as 3 components. So what's the vector form?
Just in the y.
It's yes, it's just in the y exactly. Oh well, I'm going to use z. Sorry. Yeah, I see what you're saying before. I changed my mind. I'm going to call the vertical a z because I believe that's what they do in the because they give you the t, right, or something.
They tell you the
Your
tensions.
Your Y and Z should be, X should be.
My x should be
Oh,
Your
Y
X
and
and
X.
Y.
oh okay. This is y.
Yes.
Okay.
And your X direction is in the other direction.
Oh, this way?
Yeah.
Oh, okay. That's very good. So what I've written is actually not, we should never do that because this is called a left-handed coordinate system.
What's bad about that?
The right-hand rule doesn't work.
Oh.
We have to use the left-hand rule. Well, so nothing, it's just that we get the wrong answer for everything. But not the wrong answer. Not the wrong answer because physically we're doing something wrong, but the wrong answer because when we say what direction the torque is in,
We're getting the opposite direction.
we're getting the opposite direction. Now, it's just convention, but you have to keep using the same convention. Obviously, a way we can check is with the right-hand rule, we know that this cross this is this, right? A cross B is C. X cross Y has to be Z, positive Z. So if we do X cross Y, we get Z, which is up. So this is correct. The other way does not work. I could do that and put Z down, but anyway, that's the whole thing. So force of gravity, so I'm getting lost track. The force of gravity is now in the Z direction. It's in the minus mg, right? That's it. And now force of tension is what? And they give you the vector actually, right? Or do they?
They give you the coordinates of the ends.
The coordinates of this point?
No, the point at the top of the pole,
This? Yeah.
and then its point on the ground.
Oh, so they give you those two. So
Yes.
so how do we get this vector?
Distance
C minus B.
between the two points.
Yeah, it would be right. We subtract them, right? Because we have to get actual vector. So what's the vector of that? So if we subtract the x components and the y components and the z components, we get. Well, I'll just make something up. So I'll say it's like 2, 3, 1.
Wouldn't the y direction be negative?
Yes. Yes, probably. I should really make it more reasonable.
Do you want the coordinates?
Yeah, sure.
B at the end of the rod is 377.
Oh, this is 377.
No,
No, the end of the
at the end
Oh,
of the
this is
rod.
37.
And then C
Yeah.
there is 390.
Okay. So now to subtract them. Well, oh, okay. So they're in the x component. Sort of strange. They have zero difference. That's fine. The y component they have a -2. So yeah, it is negative, and then this is going to be 7. Okay. So it's much higher, but it's a little bit off to the side. So that's f of t. And now what is the other force? Well,
Sorry, quick question.
Yeah.
Would it be -7 plus 2? Y is positive, Z is negative?
force
Given
of
given
tension. Well,
Given your
oh yeah, you're right. Yeah, you're right. Yeah. Thank you. It's this minus this.
Well, no.
Or sorry, this minus this. That's what I just did. Yeah. It's this minus this. Yeah, you're right. Because it's the end minus the initial, and we're finding this tension. Yes. Now we could negate this whole thing to get the tension from this point, but of course that's not what we want. So yeah, you're right. Yeah, it's very important because the z component we want to be downward. Obviously, we want it to go vertically down. So we have these two forces. Now we actually have this other force, and we don't actually know what it is, but we could actually solve for it. I don't even know if this is what they want you to do, but we could solve for it. I'll call it F1, just to make it stand out, because it stands out less now. Anyway, and we could find it. We just say F1. Okay, I'll call it F again. Sorry. Right? And there we go. And now we know, well, obviously the sum of the forces in each dimension have to be 0. And so we could just find it. We find that fx has to be 0, fy has to be -2, and fz has to be, mg minus 7 is 0. So whatever we get from that. mg plus 7, I guess. So whatever. But anyway, because that's fine. I don't know if I think they want you to find something with a torque, right?
The reaction torque.
Oh, the reaction torque.
Forces and torques at A.
Oh, okay. At A, which is this.
Yes,
I
on the
assume,
ground.
okay.
Yes.
Wait. Oh, what point is this? Do they tell you the coordinates? Is it the origin?
Starting at the origin.
Oh, okay. So this is 0, 0, 0. Okay. So so the reaction force. I don't know what reaction means. in
Wouldn't
this.
that just be your normal force? Like your F
Yeah,
normal?
probably. Yeah, I believe this is probably what it means. I don't know that phrase reaction force.
In this case, wouldn't it just be F? Is that as your reaction force from that point?
I suppose.
It's considering
Makes sense.
mg and the tension.
Yeah.
So it's forced to keeping the system in equilibrium.
That is the reaction
Okay,
force.
I like that.
Okay.
Yeah. We'll go with that. Yes.
Check in the box.
So there you go. Now we actually have all the forces. We don't actually know anything about the torques. Now, we don't actually need to find anything with the torques, right? Now that we do because they told us. But there's no like normally in a problem like this we would need to find this force and we couldn't do it with forces because we wouldn't know something else. And we would need to use torque where like let's say if there was another force up here that we didn't know about, often like the problem I did the other day it was like at the end of the video where if this is like you'll probably do this problem several times. Or if you've taken statics, I think you do this like 100 times, which is you have like this. You have a rod, a tension going up at some angle, but you don't know the angle or something, or maybe you do, but you don't know the tension, whatever. Something's unknown about this force. You, of course, know this and you know this, and you also don't know anything about this point, right? And you need to use, well, you can't use the forces because there's two forces you don't know about. So yeah, the sum of the forces is 0, but you wouldn't know, even if you use the x direction, this has an x component, this has an x component you don't know about. And if you use the y direction, this has a y component, this has a y component you don't know about, but you can use the torques to get rid of one of them. It's not really getting rid of one of them, it's just saying that it's not rotating around this point, so I can talk about the torques around this point being 0. And it's also not rotating around this point, so the torques around this point is 0, which gets rid of this, and you just get that the torque down from the mass and the torque up from here must cancel out because it's not rotating around this point either. So no matter where we pick as our torque sort of origin or whatever, if something's not rotating at all, then it's not rotating around all the points. So we can pick any point. And wherever we pick our point is going to have a torque R cross F, right? And if R is the distance between where the force is applied and where the force is applied and where we're considering our rotation. And if that's 0, if the distance is 0, then of course this becomes 0. So we can get
So just to clarify, we've been using torque and moment interchangeably, correct?
Probably. I don't know what a moment is actually. I hear that a lot, and I still don't really know what it is.
So when I did physics, we call this a moment on the arm when
Yeah.
you take a origin point and see how a force is causing a rotation at that point, which was the distance times the force.
Then yes,
Okay.
that's torque. Yes, yes, I've heard that a lot, and then I've heard moment arm. Is that it?
Yeah.
You heard that before? Okay, I don't know what any of those. I guess those are all torques. Actually, we were talking about how.
Because for us, torque is more of that twisting force.
Yeah.
Well, I studied in the British system, so it was
Oh,
more
they
the
have different
metric system.
words
Torque
for it.
was more the twist on an object versus.
Right.
So if you have a rod, if you're twisting it, that's
Oh.
a torque. But if you're pivoting it on one end and pushing it, that's a moment.
Right.
Which is creating torque around.
Yeah.
the
Yeah,
center,
yeah,
The
yeah.
moment
Right.
just creates torque.
Exactly. Yeah.
Yes, there's something about twisting.
The torque was
Torsion or something?
specifically used for the twisting.
Yeah, I think there's a word, not torque. but
Torsion. Sorry.
Torsion, I believe. Yeah, yeah.
That's what it is.
There we go.
I again, I don't know. I never learned any of this, but
That's along the axis, though.
Yeah.
Okay.
and then you have to use matrices and all this bunch of stuff, right? Anyway, a lot of fun. Anyway, so also we were talking about the there's another thing that sometimes they teach you about like in like high school or something, or they'll say like, well, there's a force here times the distance. Well, this is called like the lever force or whatever, or like, and if this is twice as far,
Yeah. We have to wait.
right, then you only have to wait, and they call this a new it's the lever principle or whatever. There's actually like I think
We
page called.
studied that as moment principle.
Okay, this is literally just torque. Yeah, so yeah, it's all the same thing. So you might have heard about levers. Everything with levers is just torque, right? It's just that in these cases it's much easier to do because all the angles are, first of all, it's in a plane, and all the angles are 90 degrees, so you don't have to worry about the sine theta part. But yeah, okay, so let me write this. Okay, this is not, I should really write this. This is the magnitude. So in this case, if we just had, okay, well let's just find the torque, I guess. So these are all true, that's fine. I'm going to erase these because what we really want to write is the torque, which is R cross F. Well, the torque around any point has to be 0. Where to know that? Well, sorry, this is not correct way to write it. Torque is a vector. So there's 3 components, and they should all be 0. This is the same statement as I just had with the forces, right? I wrote 3 equations. We can't actually break this up. I mean, we can. We can write Tx equals 0. Tau, I should say. Tau x equals tau y, so it's fine. But this is really important. Tau x is not Rx cross Fx. Okay? You can tell this is the case because these two are in the x-plane, and 2 things in the x direction, actually, I should say. These actually are parallel. They're actually parallel vectors, and the cross product of things in the same plane are 0. So this is always 0. So this is not true. Technically, there is a way to write it, and it's like, I don't know, this plus RZ cross whatever. It's complicated. Don't do it. The point is, I would just write it like this, and then you find you just do it all at once. I mean, it's the same. It's not any harder, right? You just are going to take R cross F, and so, well, it's actually, sorry, it's going to be the sum of R cross F, all the forces. You can even write I and I, because they're the same one. And if we are talking about, let's say we're talking about the torque around point A, which is probably one of the ones they want you to do. Actually,
So,
yeah.
Sorry, so R is the position vector and F is the force vector, right?
R is the position vector and F is the force. Yes.
So, is a position vector, I might be confusing this with the unit vector, but I always thought that a position vector indicated that which direction the force was going more than...
R is the vector that goes from the, actually, I'll come back. I'm
Okay.
confused about this problem, but I'll come back to this problem. The position, so if we are applying a force here, right? And we want to find the torque around this point A. The torque around A would be RA, shouldn't write A, R cross F, where R is the vector that starts at the origin meaning where we're taking the torque around, and it goes to where the force is applied.
I see.
Yeah, so it's this vector. Yeah, it's not the vector that about the force. Right? The force vector is its own thing, but the force vector is of course applied at a different position than the where we're measuring the torque. If it's not, then there's no torque there. And actually, so if we want to find the direction of this, which is actually another step I should have mentioned before, we would take R cross F, which is R cross F, which is this way. It's hard to see. It's this, right? R cross F. And we would get the torque vector, which goes into the board. The torque vector is located at this point. Remember, all vectors are located at a point. Okay, that's not quite true, but we'll just leave it there. It's located here. You can just write it wherever. And it goes into the board, and so we can write it like that. Did I tell you about this? This is like supposed to be like an arrow, that sort of rear of an arrow. Like an arrow is... Yeah, exactly. Like it's supposed to be like, if an arrow looks like that, this means it's going into the board, and this means going out of the board, because I guess that's what it looks like if you... Anyway, whatever.
Getting shot with an arrow.
Exactly. This is what you see right before you get shot in there. So, anyway, so we can write this. You can... It actually might be even better for you to just write literally the words into the board, or into the page.
Maybe just include little legends.
Yeah, you could do that too. I mean, most books and stuff won't even bother doing this. They'll just write into the page or out of the page. Out of the page means toward you, just to reduce ambiguity. So this is into the page, yeah. So, and notice that the important part is that if you do all these problems that I was just showing, they're all in the plane, right? And somehow I've been doing, so they're all in the plane, and when I do it, here's an interesting question. When I do them as force problems, there's two equations we have to solve. There's the vertical ones and the horizontal ones, right? Or we can break it into however we want. So that's two equations because there's two dimensions. But somehow when I do them as torque equations, of course if I choose one point, I don't, or just choose one point, somehow I only get one dimension, right? Because things can only apply torque this way or this way. There's not two directions of torque. There's clockwise or counterclockwise. That's one dimension, right? And that's exactly indicated by this. Anything on a plane, the cross product is always going to be into the page or out of the page. That's one dimension. So the entire all torques that you're doing in a flat plane, which is most of them that you'll do, are actually a one-dimensional problem, and it's actually in the mechanics when they write equations like this, right? Which you don't use this that much, but this is the kinematics equation, but in a rotating direction. This actually is a one-dimension. This is one dimensions, as we know, but it's actually in the dimension of into the page. It's technically by convention. That's what we call it. It's because of the right-hand rule. If something, so this another way you could say it is that this is going to want to rotate something this way, and so by the right-hand rule, it's going into the page, which is the same thing. So anyway, so by convention, that's the dimension we actually talk about the kinematics, and that's the dimension everything happens in. Of course, it's easier just to imagine it's rotating. But you can't actually, anyway, yeah. So, all right. Now, this is where I didn't understand this problem the first time, and then I thought I understood it, and now I don't understand it again, which is that if we consider the forces applying right at this point, this somehow can't possibly be true. Because around this point, there's two torques going downward, and there's no torque going upward. Just for example, just take the z direction. There's no torque going upward. So this is impossible. This isn't I'm not joking. This is literally impossible. So I don't know what they want you to. Well, okay. So when I say impossible, I mean the way I've drawn it is impossible. I think what they want you to say is that because this is like screwed into the ground or whatever, they want you to say that like the origin is here, but there's a force applied slightly far away from it. I know it's like ridiculous. There's no, how would they possibly, but okay. Well, actually.
Should we be considering
Actually, we can do, okay.
Not enough information to solve the problem.
Yeah, actually, we can't, okay, so here's the thing. if we'd assumed that the force was applied right at the origin, where they say that that's where it's fixed and stuff, we can't, if we pick that to be our torque point, we get two torques, and they're both, just for one example, going vertically downward. That's sort of not a torque direction, but you know, it will end up being a torque going like in this way or whatever, right?
Yeah.
And so that's impossible. Now, what we could do is just say, why don't we pick this point as our torque point? That way we'd have no torque from the rope, and now we get torque down must be canceled with some torque up. Now, we don't know where it's applied. We don't know the distance. We don't know any of that. But we can actually solve for the actual torque, which is actually okay, I see what they're saying. The reason they want you to do this problem is because they want you to see that there's a torque that we can't associate with a force. And the reason we can't, well, actually we can. So we could solve for this distance.
Why can't
Wait a minute.
Yeah.
figure that distance out, right? Because that's
We can be-
origin. If you're
Yeah.
if you're taking the torque at where the force T or tension T
Yes.
is, then can't you figure out the distance from 0, 0, 0 to 3777? And that would be your distance, the R and F, R plus F.
You said you could do that.
The length of the rod would be your distance.
Yeah, no, but that's this distance. If we
Yeah.
assume it's the full distance,
Right, and your gravity is force of gravity is acting exactly at the center of the rod.
that's right. That was what I was going to do. Then we get the torque. We get the torque caused by this. So we get torque at this point.
Yeah.
But that what I'm saying is that if we computed the torque around this point, if we assume that this is all at this point, these don't cancel. So somehow the setup involves this torque being applied by a force that's not exactly at the origin.
I thought you were calculating torque at
Yeah.
the point where T is acting.
No, well, yeah, but both of those should be true. I'm just saying, if I can come up with a situation where it's impossible, it's impossible. You're right that that's what I was going to do.
Okay.
So, but then what I just thought about is what we could do is once we find the torque around this point, so in other words, it's just, we only have one torque going down, one torque going up. We have a torque at that point, and we have a force at that point. Therefore, we could find we could then consider this point and say that these must be canceled by a force applied at some distance, r, away from the origin, and it would be very small probably. Now that's a stupid problem. That's really silly, because that involves a very small.
Sorry, what
Yeah.
are we trying to find?
I don't know. Well, what, okay, the problem I'm trying to find, yeah,
Does it change anything that we have a force of 2 kilonewtons on the rope?
oh, this T?
Yeah, that,
No, no, because we'll just use that in the problem now. Yeah, so T is actually, sorry. So, sorry. It's this times 2
That.
kilonewtons.
okay.
Yeah. So that's what it does. Yeah, you're right. I didn't actually write. Because this is a force, these are numbers. So I should have written this, yes. So therefore this will have units of, yes, exactly. So this will have units of newtons or whatever. Yeah, so the point is that what all I'm trying to say is that if I believe what they, maybe I'm assuming, but I believe what they want you to assume is that this force is applied right at the origin. But we actually can, it's not, it can't possibly be applied at the origin because then these two will not cancel anything. Right? These, in other words, if we find the torque around this point, it should be 0. And these two, it's not, unless it's supposed to be falling, which I don't think is the case. So, but what we can do is if we can find the torque and the force at this point, right? Yeah, okay, I think it's still impossible. But if we find the torque and the force at this point, of course, we can use this to find the R. But then, of course, to find the torque, we actually had to assume that this was the total distance, which is not actually true anymore. So it's impossible. But it can be approximated. This is a bad problem. What all they need you to do, the thing they actually need you to do though, is find the torque. Let's just do that now. I'm going to stop talking. Let's just find the actual torque, and not consider the problems I just laid out. We just do basically what you said, where we take this point as our origin.
Okay.
And we-
Does it change if you assume A to not be in the middle, but at the bottom where the rod is resting?
If you assume A to be what?
The bottom corner of the rod?
Oh, like down, like
Yeah.
this part?
Yep.
Yeah, but then we have to worry about like,
The diagonal distance.
yeah, now we're getting into like,
Right.
this is a lot of,
Never mind.
no, it's, I don't-
Just do it just like a line.
Yeah.
no, but, right, but, that's what I assume, and I believe the correct way to do this problem would be like really getting into the physics of the engineering of a threaded rod or something, which is not at all interesting to me. So I'm not going to do it. But let's just find the torque. How about this? So torque is going to be, it's going to be, we're going to pick this as our starting point. We actually want to find this point here, which is going to be, it's half of this, right? Because it's basically the average between the origin and this is this point here. So the actual point it's applied. So I'll erase this for now. I'll just write r of gravity. So this is the vector that goes from our origin to this point, right, where the force is applied, and that's going to be minus 3 halves, minus 7 halves, minus 7 halves. Is that right? It's just half of this. If you made these positive, it would be this much, and it's half of them. Or sorry, yeah, if you made this positive, it would be right here, and it's the negative of that. So
RG being r gravity.
yeah, that would be the vector. That's literally this vector right here.
Okay.
We know that it's negative in all three components because it's opposite a vector that's positive in all three components. It's exactly negative of it. So that's RG. Now we can find the torque due to gravity. It's literally just RG cross FG, which is this. And now we have to do an actual cross product, unfortunately. So I'll write it all out here. If you know a shortcut, you're free to use it. It actually becomes a little easier because there's a bunch of zeros. So we wrote our R vector here, and we wrote our F vector here. Make sure, of course, that it's all in the same, we have the X components and the Y components and the Z components. And then we get I times, and then we have, so it's I hat, and it's going to be this times this, minus this times this. Now this times this is 0, minus mg times minus 7 halves, which is plus 7 halves mg. I'll do that again.
Please.
So what we did is I took the first entry, I hat. This is how you do a determinant of any matrix, by the way, but in this case we have an I hat here. It's this times the quantity. It's actually the determinant of this little matrix, which is this times this, minus this times this. This is a 2, 7 over 2. So it's this times this, which is 0, minus this times this, which is plus 7 halves mg.
Okay, thank you.
Right, and then I'll do the whole thing, and then I'll go back over it again. And then the second time, we have a minus. Just trust me. It's this is the one you have to remember. It doesn't make any sense. We have to memorize it. And we get now it's this matrix. It's always the matrix that excludes. I couldn't think of the opposite of includes. Excludes this column and this row.
Mm-hmm.
So it's this matrix with these 4 things in the sort of edges. So it's this times this, which is 0, minus this times this. So we have a minus, and then it's the same thing, mg 7 over 2. It's the same number. Shouldn't have written it differently, but
3 over 2.
oh, sorry, 3 over 2. Yeah, you're right. Thank you. I was gonna say, but yeah, you're right. Yes. And now plus k hat, and now luckily, because we have zeros here, this times this is 0, this times this is 0, so we get 0, so there's no k direction. Which actually makes sense because one of our input vectors, the r, was, the f. Oh, I did this backwards. Sorry, these two should be flipped. But all that does is actually give us minus signs everywhere.
So they're all supposed to be negative?
I should negate everything here, sorry.
Why are they flipped?
Because r is supposed to go here. So it's r cross f.
Oh,
Oh, the
The
whole
rows
line.
are-
Oh,
sorry,
the rows. I
flipped.
thought you meant the 7 halves.
No.
Like, whoa.
No. It's just the rows are supposed to be flipped. If it turns out if you flip the rows, you only get signs different. So I'm gonna fix it. Sorry about that. Minus this is R, and we get that, right? And we can, so I'll do it again for real now. So we have I hat times the determinant of this matrix, which is this times this, which is plus 7/2, minus 0, good, minus j hat, you always put a minus in the second one, and the fourth one if you had one, and the sixth one, etc. But we're only going to have 3, really. So minus j hat, the determinant of this matrix, which is 3/2 mg, minus 0, good, plus k hat times, those are both, this is 0 and this is 0, so it's 0. So we get torque of due to gravity is, and so this is the I component, 7/2 mg, right? And the j component is minus 3/2 mg. And the k component is 0.
Why'd you take that around B?
Why'd I take,
So technically, like the fixed point is A, the top of the rod is B, and
Yes.
where the rope connects is C.
yes,
Why'd you take it about the point that's not fixed?
you mean the end of the rod?
Yes.
Because I want to find the torque on the rod due to the force, the torques that are not this tension.
So do you have?
I'm just trying to find this one specifically is the reason.
Building on her question earlier, so I understand, like, in a free body diagram, what constitutes a force.
Yeah.
But when they're saying what constitutes a torque, it's a little more complicated because it's two forces acting on something, right?
It's
You
one
need- you
force
need-
acting on something.
But you need two forces to make a torque, right? You need R and F.
R is not a force. R is just a distance. So this distance here is just a measurement of the distance, which is a vector because it's a.
Okay, you need a certain distance and you need a force.
Yes,
in
you always
order
need
to
a
make
distance away. You can't have a torque of a force like it's like pushing on a door at the hinges.
Mhm.
It creates no torque
Okay, so in that case, you would.
because there's no R.
This system right here has 3 torques on it, then, right?
I wouldn't say that. I would say it has. If you, it has 3 torques about this point. A torque makes something want to rotate around a point, right?
Okay.
And so around this point, which is just a random point, it has 3 torques on it.
So if we get to pick the points, we can determine how many torques we're solving for.
Yes, and of course we can't make it less than 2, because if we pick this point, which
Then we
is what we're doing now, we have 2 torques.
Okay, and if we pick mg, then we've got the 2 torques on both sides.
Exactly. And if we
Okay.
pick the origin, we have 2 torques,
The
Right.
mg and the.
which this is the part that doesn't make any sense. But yeah,
All right. So what about this? Doesn't make any sense then.
because if we pick this point,
Mhm.
we have 2 torques, and they have, just for example, they both have a negative k component,
Okay.
and that has to be canceled by some. It's not accelerating downward, right?
Oh, I see.
So that doesn't make any sense. There must be some torque applied here, but of course it can't be applied at the origin because then it would have no torque. There has to be some torque applied some distance away from the origin that they're not telling us.
But because it's a fixed system, wouldn't that impact it?
It's fixed because the torques are balanced. That's what fixed means. Yeah. Now we found that
Okay.
because
I see
it's
what you
also
mean.
not accelerating linearly with just forces, so forget about torques, just with forces, there's only 3 forces on it supposedly. So they say. And now if there's only 3 and we know explicitly 2 of them, we know this tension, they tell us. They tell us the magnitude and they tell us the direction, so they tell us the tension. They also told us, we know there's gravity. And if there's only one other force, we literally just solve for. I mean, I didn't write it out, but like it's just this plus this plus this is 0.
Okay.
So we explicitly get a value for the force here. Now the place I have an issue with it is that they seem to think you can assume that force is applied right at the origin. But I'm claiming that isn't possible because then the torque around this point would not be balanced, and therefore it would be rotating around the origin. All right, so that was my issue. Now they don't. Now what we could do. Well, this is what. I'll finish this and I'll say what we could do to solve that. Yeah. So we get this. Oh, actually, we did finish it. We got this torque due to gravity.
Okay.
And now, of course, the torque due to there's only 2 torques, and if it's not moving, and we have 2 torques. The other one is just the negative of this, right?
Mhm.
That's it. So the other one, so the torque due to, I'll call it due to F. F meaning the F at the at the origin, quote unquote, should just be negative 7 halves mg, positive 3 halves mg, 0. Yeah. Now, you might be thinking, wait a minute, how come we got the torque to have 0 vertical component? This is the vertical component, right? The z component. How come we got 0 vertical component here? That seems a little weird. It should have some vertical component. Remember, this is the torque vector. In the torque vector, the z component means this way, and therefore we're talking about the torque vector in the z direction is talking about rotation this way.
Spiraling out.
Right, so in other words, this applies no torque around this way, which kind of makes sense, because why would it? Like, it sort of doesn't seem like it should. So that's a quick thing. When we're talking about forces, we can literally talk about this makes things go up, this thing makes things go to the y direction, this makes things go to the x direction. In the torque vector, they don't. They make things rotate around these axes. So this 0 means it's not rotating around this way. Well, it's not rotating at all, but it's not trying to rotate around this way. This means that it's trying to rotate this way, which is, I guess, reasonable. And this means that it's trying to rotate this way, which is also, I guess, reasonable. Yeah.
So
Trying meaning that if I turned off this, that's what would happen to it.
So that all makes sense. My question is, do we account for the fact that there's an angle on the rod?
Yes, we did,
It's not-
because we used the r vector to be this.
which was just the
This has 3 components, so this is a vector that goes from the origin to like there in 3-dimensional space.
right, but your forces are still acting at an angle to that. They're not perpendicular to that.
Oh, sorry. Yes, because when we took the cross product, this is equivalent to the magnitude of Rg times the magnitude of Fg times sine of theta, where theta would be the angle. It's really hard to do things with angles in 3 dimensions. Well,
Okay.
it's not that hard. I guess you just take the dot product.
So we're
Divide by
going
that.
to assume we're going to assume that the forces are perpendicular.
No, it doesn't assume. This, when we do the cross product, this answer takes into account that they're at angles. Yeah. The cross product is instead of this. This is built into this. Yeah, that's a good question. Yeah, we don't assume that they're. So I drew them a little misleadingly. I drew them as if it's 90 degrees, but it does not have to. If we use this, it always
Already
works.
works.
Yeah, because the angles are. We didn't. It's actually. Yeah, again, it's kind of hard to.
So
Yeah.
in this case, we've selected mg to be the point of origin, right?
No, the 0, 0, 0 was the point of origin right here.
Okay, so
Yeah.
If we selected 0, 0, 0 to be the point of origin,
Oh, sorry.
The
I
point of
said the
rotation.
wrong thing. The point of rotation. Yeah, you're right. The origin of just our whole system where we label things is this.
okay, that was
I said
that
the
was
wrong
bad-
thing.
That was bad on my part.
No, you said the right thing, and I was thinking of the wrong thing. The point of rotation that we're considering the torque around is this point in this particular, this T. This TG is the torque from gravity around this point here.
Okay, and in that case, so for the other one, torque F, that's at point A.
That
F
is the
point of
torque.
origin then, right?
No, that is still it's still the, because we said the sum of the torques around point A. This is, sorry, around. Yeah. Around point, I guess this is B, right? Is that what it's called, B?
Yes.
This is point B. So the sum of the torques around point B is 0 because it's not rotating around point B. Good. Therefore, the torque of gravity around B, which is this, that's what this is, right? I really should be writing B because it's not the same as the torque of gravity around a different point. Torque of gravity around B plus the torque of F around B must be 0. Therefore, if we have the torque of gravity around B, which we solved for, we can take this just the negative, is the torque of F around B. Yeah, so that's a good point. We really should be writing, every time we write torque, we should be writing, obviously, what it's from, which is gravity in this case. We should also be writing where it's acting, because that's very important, because later we might do another thing. I don't want to because I hate this problem, but later
Same.
we might want to do another thing around this point where we talk about the torque of gravity, and it's completely different. It's absolutely unrelated. It's not going to look like this. It's not going to have the same components. It's not going to be anything like that. So we would have to completely redo it with a new R vector. It might not be completely different, actually, but actually it isn't. It's going to be the positive, the negative of this. But anyway, it doesn't matter. The point is that it's a different, completely, it like lives in a different space. That's what you should think of it as. The forces all live in the same space. All the forces acting on an object kind of live in the same space. You can add them. the torques due to different objects live in completely different worlds, right? You can't add them together. You can't compare them. You can't talk. They're completely different vectors. So the torque of anything around point B can be only added to other torques around point B, and you can take the sum and set it equal to 0 if you know it's not rotating around B. Yeah. So anyway, so now the thing I was trying to say that I won't really do this because you don't have to do this with the homework. You do this, but you don't have to do what I'm about to say, which is that now that we have the torque at point B, and we have the force acting at, sorry, what am I doing? This is the okay, what am I doing? This is the torque. Oh yeah, I guess we still can't solve for it. Never mind.
So,
Yeah.
Sorry. So I know that the two forces up there are the forces that are the reaction forces, right?
Well, I don't know. I think this might be the reaction force.
Okay, but isn't that the same thing as Ft and Fg,
That's
just
reaction
specifying what they are?
I don't know. I don't actually know what the reaction force is. I don't know what that means. I assume that just means all the forces, or the one that.
I'm
Mixed in
guessing
equilibrium,
it's
like you
the one
said.
that's acting at the
Yeah, because
point.
that's the one you don't know. So don't tell me these we know. I mean,
Mhm.
don't tell me that you found this because yeah, I know. But but this. So there's So we found this by literally we wrote gravity because we know what it is.
Okay.
It doesn't have. Remember, tension. We know where it is because they told us. Well, actually, they didn't tell us. They told us where it acts and where it ends, and the tension must be along the rope. Obviously, that's how tension works. And so therefore we can subtract them and get the direction, and then they told us the magnitude, so there you go. And now there's only one other force, so they say, on the system, which is some, I guess, reaction force. Yeah, I guess that makes sense.
So what would F be in this case then, all the way by point A?
That's this. This is F at point A.
Okay, and these are all acceptable answers because we can't figure out what the forces on A are without more information.
No, we can figure out what the force is at point A, because the sum of these three forces must be 0.
Okay, so they're all at rest. Okay. That's
Yeah,
easy enough.
everything's not moving right. So the sum of the forces is 0. So I just didn't write the answer, but it's 0, minus 2, 7 plus mg, right? That's the answer. So that's F of A. That's fine. When they say so that answer is no problem
Okay.
because we don't need to care about the pivot or anything like that for forces, right? We know that it's not accelerating up or down or sideways. So that's some of the forces is fine. Some of the forces is indeed 0. Some of the torques we can do around the end point, and therefore we get this torque around that point. And I believe that's sufficient for the answer. I had a bit of a problem with the fact that we cannot do the sum of the torques around this point for a reason that seems mysterious. It's not actually mysterious. It's just wrong because I hate when people say things like that. But it's because if you imagine like a rod like this, okay, and you push it down, this is literally the exact situation we have. It clearly has to be like a lever with my hand. I have to put my finger here so that I'm like kind of applying I'm applying a torque with my finger. I can't just like hold it like a pivot. It can't just be a pivot. It has to be like a lever like that, right? So intuitively, it doesn't even make sense that it would. That's why the other day when I was looking at the problem for the first time, I saw it and I was like, this doesn't seem right because like, do they mean something's pulling it up? Like that would make more sense. Is that you like with the thing I showed with this problem? This makes sense. It's clear that what's happening here is kind of mysterious. I don't quite know. Like it seems like it probably has some forces inward and some forces upward from friction, but it's a little hard to tell. But I clearly have a force up and a force down and gravity. Like it's sort of clear that things are balanced. This one, it doesn't seem like things are balanced. So that's why I have it, and I don't think they are. But yet we can just solve for these. We can solve them without worrying about that. But yeah. Does that make sense? Does it make sense why I'm confused by this?
Mm-hmm.
Yeah.
It's sort of like there needs to be some kind of leverage keeping it up. Why is it not just falling on the ground?
So you want like the torques at point B and then the force at point A?
This is the. So this
For
is
the
the.
answer,
Sorry.
just to make sure.
Okay. This is going to make it more confusing. This is
Great.
technically what
Cannot
it is.
wait for that.
It's actually this. It's the torque due to force at A around point B.
Okay.
Okay? Now,
Can't you just say?
Yeah.
the object, we have, torque is equal to I alpha.
Yes.
We have no alpha.
0.
Can't we just say torque is equal to 0?
Yes, that's what we
call it
did. That's
a day?
this 0.
And then, yeah, but we don't have to go into all of this other stuff.
Yes. Yes. I solved everything without confronting the actual issue. But it is true that the situation they've given us is not possible. And the reason is because torque around this point should be 0 as well, and it seems to be impossible to solve that.
Yeah, that stuff's right here.
Yeah, what
Yes.
direction would the angular acceleration be in the move?
Yeah, so this is where, did they say there's no friction? I forgot what I said last.
No, you considered it.
I considered it. We could say there's friction, but not right now.
Okay.
Let's just say that they're rotating. So I think this is the first one. So I think this is supposed to be relatively simple. Like, they don't want you to worry about balancing friction stuff, but we'll consider that. But what would if this was going to act on this? So this is a yo-yo, right? It's acting like here. What direction would it want to rotate if you just let it go? If there was no friction? This way, right? And now let's use the right-hand rule. Curl our fingers this way. We torque outward this way. Yes, around. Of course, we're assuming it's rotating around the center. Oh no, sorry. That's what I would miss the first time. They want you to find the torque around the point, I guess. Point at the base.
Around the point.
Torque on the yo-yo due to
Yeah, but you had said that they
string around
specifically
the point
wanted
of
it at a
contact.
radius.
Yes, around the point. Okay, sorry. So that was all totally valid, except that was for the torque.
Oh, that right, like on the ground. Yes.
Yeah, that was the torque around the center. Now for the torque around this point, well, I don't know. You can kind of imagine it's like going to be the same thing, right? Like it's going to still want to go this way. And we can zoom in and kind of look at the real reason why. R, T. Okay, so that's R. So R, remember, is from the base too. So this is the, Right, this is this. Okay, and now, I mean, I guess you could then say there's a theta there, and it's TR times sine theta, which would be positive, because sine goes like this. So up until 180 degrees, it's positive. This is not a good way to explain it. Okay. So, yeah. So it's positive, and so therefore it sort of follows the same direction. Positive means is this counterclockwise, right?
Yes.
Counterclockwise. So because we can just use the right-hand rule. But yeah, so that's what I meant to do. Sorry, that's what I meant to do, use the right-hand rule. So let's use the right-hand rule and just say, well, R goes like this, and T goes like this. Now, of course, it doesn't really matter what angle it is because we can break it into a component, right? We can, if we really wanted to use the true right-hand rule with perpendicular things, we can actually say this T has some component along here and some component this way, right? Now, the component along here, of course, is not going to contribute to torque because that's like pulling a door away from the hinges. That doesn't open it. But that has some component along this way, and that component is indeed going to go. There's R cross F is T, and it goes out of the board, and out of the board corresponds to this rotation. So the torque is out of the board. That's the torque vector, so we could write that if we want. Okay, so that's that one. I'll go back and talk about friction in a second because it's important. It's not it doesn't matter for this problem, but I'll just talk about it because it's a thing that happens.
So how does the torque in this case and the angular acceleration is this problem saying that that they're both the same?
They're the same direction.
Okay, so
Yeah.
Yeah, because the force, yeah. So R is the same thing, but since force goes in the direction of acceleration, torque and angular
yeah.
acceleration are
Yes,
okay.
yes, exactly, yes. So in other words, when I said rotates this way, I was really talking about the torque, but the angular acceleration is also in the same direction.
All right. So when you use the right-hand rule, I see you doing this, and I see you doing
Yes, they're both.
this. They're both applicable.
Yeah. So when something is rotating like this,
Okay.
this is not a vector because a vector can't turn. Okay. This rotation corresponds to a vector going out of the board,
Okay.
and this corresponds to, so I'll say out of board, and this is into board.
Okay. So if it starts moving to the right, then we assume that it's rolling this way, so it's like this. And it comes punching out.
Sorry,
it
you're
says-
talking about rolling.
Yeah, so what if the OU begins to move to the right? So if it's going
Okay,
to
so
the
there would
right,
have to be friction then.
What?
But yeah,
Mhm.
that would be a whole. Yeah, if it was going to the right, that means that it's going this way, right?
Okay.
Mhm.
And so therefore it would be going into the board. We could figure that out by using the way your right hand fingers curl and then your thumb is going.
All right.
So this is a convention. The fact that this and this are the same, this and this is the same. This is a convention. This doesn't really mean anything.
Okay.
But the way to remember it is with your right hand. That's similar to the cross product rule, which is that this. The cross product right hand rule is the same. It's actually the same convention, but we don't have to get into why they're the same. But this means that if you have some vector r and some vector f that create a torque, of course it involves the cross product, and so you use this, pointer finger or whatever as the first vector, second vector, and then this is the direction of the third vector.
All right, so
Output.
so r in this case being the first vector, it's like okay, first vector, second vector, then this is what's left over.
This is the torque vector,
Okay.
the output. Yeah. So of course now if they're in the same direction, there's no, it doesn't
Then
work.
just-
It's
yeah.
zero, in fact.
Okay, and then we just use this.
Yeah, and that's for if you go from now, right? So we could. So I was showing you. There's two ways to do this. One is we could imagine what way it would go. Forget about friction. Pretend it's just going to spin. Okay. This torque would make this thing around this point. It would make something spin like this, right? Like it properly. You can't. That's not very precise, but you can kind of imagine that's what's going to happen. And this way corresponds to a torque out of the board. We could equivalently consider that as the actual formula where we have r and f. Now r is this vector, f is this vector, and we can use the right-hand rule and we get out of the board again. Of course, if we really wanted to be precise, we could break it into the components that are perpendicular. Now notice that when we break into the components, this component here is actually t sine theta. So this is actually rf sine theta.
Okay.
So the angle between them involves a sine theta. Sorry, if we use the angle between them, we would have torque as rf sine theta, the magnitude. If we break into components, one of the things gets a sine theta, and it's just r times f, right? So those are the same thing. Breaking into components and the cross product thing is the same.
But it says right here that since we're assigning the point of contact
Yeah.
at the table, that friction is negligible. That friction doesn't have to be considered.
Yeah, no, you're right. Exactly. Yes.
Okay.
So that's why it doesn't actually matter in this case.
Okay, so the point of contact is a strategic sort of thing where,
Yes, exactly.
okay, if you position it so that it's in contact with the most forces, those are the forces that you can neglect because
R is
torque
zero.
only applies, okay, because R is 0 and so torque would be 0.
Exactly. Yes.
Okay.
It's strategic. That's
Okay.
a
so
good way
it's,
to put it.
so it's more like a game in this case.
Yes, exactly, because it's not rotating around any of the points. So
Okay.
all of the points are valid places to put the torque around, and you get some of the torques is 0.
Okay, so following.
Well, actually, sorry. In this case, you don't. Sorry. I said that I didn't say that correctly.
okay.
In this case, it is rotating, so that's not true. In statics problems, what I just said is what I meant, but where it's not rotating around any of the points, so we can always pick any of them. In this case, it is rotating, but we don't actually because we're talking about the instantaneous values because we're not considering when it rolls and stuff like that. You can consider rotating around a lot of different points. You don't just have to say, oh, it's rotating around the center or rotating around here. It depends what you mean because instantaneously it has some instantaneous movement. Could be around any point. So you could always compute the torque around any point. So yeah, and in this case we do want to consider that because we don't want to talk about the friction because it would be just a little more complicated because then it involves the friction would create some kind of torque. Like if we had some force here that creates a torque kind of in this direction, right? And of course that really means out of the board. Then it would want to spin this way, right? It wants to look like this, but if it is going to roll, then friction has to apply some torque in the opposite direction. Yeah, in the opposite direction so that it actually rolls. And so the friction is going to be like that. So this is, of course, I'm considering the torque around the center now. If I was considering the torque around the bottom still, I couldn't conclude anything about the friction. Anyway, that's beyond, this problem doesn't ask for friction. So.
Okay, so because even though it's rolling, we're focusing on the instantaneous motion of the roll.
Yeah,
So we can assume can make the similar assumptions to a statics problem because of that.
No, but sorry. Okay. you can't make something like a statics problem, but the reason I said instantaneous is just because I think maybe your intuition might be, well, it's not rolling around the bottom. If it rolls, it's going to roll around the middle. So shouldn't it be 0? And that's not correct. Because instantaneously, of course, in the next instant, there's a different point that's at the bottom. Right, that's kind of the point.
Okay, I
Is
see
that-
what you mean.
Is the point of contact where like T is attached to the center?
Where T is attached to the...
The
What do
direction
you
of
mean?
the torque on the yo-yo due to the tension on the string calculated around the point of contact. So when,
Oh, contact with the ground, I think they mean.
okay,
Yeah, if they said around the point of contact of the string, it would just be
Yeah.
0 always.
okay.
So, I mean, perhaps they would ask that, but I don't.
I mean,
Don't
I
answer
know.
that question. That would be too easy.
I don't know because
Like, I wouldn't put it past, but no, I would say they mean because they actually they put a little dot here.
Okay.
So I think they mean that because that would be the relevant point when you're considering something that rolls. Like, which way is it going to roll?
Okay.
Okay, and then sorry, I didn't do this one. So this one, again, we can kind of do R cross F. R is like that, and F is like that. Okay. Yeah. For some reason, I'm confusing myself. So we have R cross F, so we get torque into the board, and into the board involves rotating this way. All right, so it's going to roll this way. That makes sense. Now that seems a little counterintuitive, but
Wait, it's gonna
It's
roll that way?
Because
Yeah.
about the point on the ground.
yes.
Like naturally you're gonna think about it about the point in the center.
Yeah.
But ignore that there's like a circle in the middle there. Just think of it, if this is my point and I'm going this way, I'm gonna want to naturally track that way.
Yeah, because in other words, forget about the center or whatever. Just think, I'm pulling this like that. How is it going to want to go around this point? It's going to want to go like that. Again, this is why I said instantaneous, because of course it's not actually going to go into the ground.
Right.
But instantaneously, it's going to go that way. Like if you think about like the next instant, it's not going to go away, right? It's going to go toward this way, and that involves a circle like that, which is into the board, the torque into the board.
And don't think of it as a disk. Just
Yeah.
think of it as think of like the distance from the contact point to
Yep.
where the torque is pulling through
Yep.
as just a lever.
Yeah, that's a good way to, because this is if we forget about the disk pieces,
Okay.
we just have R and we have F, right? Don't worry about the whatever else is happening, right?
Okay. So for the first one, I'm a little surprised that it's going out of the board. I would have thought that if the tensor force was going up, that's I imagine it wouldn't really going anywhere because acceleration is on both sides, right?
What acceleration?
For case A, it says that there's acceleration going to the left and going to the right.
Oh, don't listen to them.
But if it's going up,
Right. Okay.
Yeah, but it's going up, and it can only pivot relative to the ground, and
okay,
so
in that case, it'll have to go to the
it'll
right.
have to roll, and then you'll get some net acceleration. That's beyond they don't ask you about that in the question, but yeah.
Oh, I see. So if the tensor string's on the right side of it, then that means it's going to be rolling to the left, which means that
Yeah,
it'll
probably.
be going out of the board.
Yeah.
Okay.
so the angular velocity would be to the left for the first one and to the right for the second.
Because they're rolling
angular
in different
acceleration.
directions.
Accelerate, yeah,
Yeah.
that's what I meant. Sorry.
Yeah. No. Yes. Now this is a little counterintuitive. Yeah, the same thing because you'd think, well, aren't I like if I kind of pull a string, it should kind of go away. I don't know. It just
Yeah,
seems like it would
that's what I'm
unravel or whatever. But what you really should think about is you're literally just putting a force on something to the right.
Mm-hmm.
Like there's no forces to the left, so how could it go to the left? Now, of course, once we include friction, there will be, in fact, forces on to the left. But
Okay.
actually, I don't know if that's true either. Anyway, yeah. The point is, well, actually, okay, yeah, I'll stop there. If there was no friction, what would happen? If there was, it would just slide to the right, of course. If you turned up a little bit of friction,
Then you
Just roll.
it should still slide to the right, but maybe it would start rotating a little bit.
Yeah.
You should think of it like no friction and very little friction are very similar.
Mhm.
They're not actually right. If you turn, it shouldn't be like if you turn the friction a little bit, it goes the other way. There might be a point where it does, But generally, when you turn the friction from 0 to a small amount, it should roughly do the same thing. So if you turn a little bit of friction on, it should still go to the right, and it'll maybe slide and roll a little bit. Right? If you turn it up a little more, it might roll a little more.
Trying to think of the first one as a lever, like she said.
Yeah.
Now that confused.
Think of it as a lever like this. This is the relevant part of this picture.
Yes.
The wheel doesn't have anything to do with the, yeah.
So the second one where like R and T and then this is coming out of the board, right?
R and T.
Supposed to go in.
Wait, for the first one.
Oh, the first one.
Yeah.
R and T, and so out of the board. Yeah.
And then R.
And they're already perpendicular, so we don't need to do anything.
really bad. Do the second one again? Say it again.
R and T.
R's
Right?
going up, T's coming at this way.
Right. So this goes
And
No,
the first one,
F, sorry.
F,
The
what
first
is
one
it?
is like this.
T's going up.
This is
R. R's at the
this is
right
R,
of.
this is T.
Oh, I get you. Okay.
And the second one
Are your hands shaking yet, Keegan?
From the sugar?
What is
Getting
that?
there.
Okay.
I don't know.
PV donut.
That's a monstrosity is what it is.
It looks like
Where is it from?
diabetes in a
PV. Yeah.
Did Sean give you that?
Yes.
Seems like
Go to. You been a Blackbird?
shot. Mhm.
Oh. Oh.
Oh.
Better than that.
Oh, in Fenway? Is there
Yeah.
another one? Oh.
One. That's the only one I know of.
Like a pastry shop or a cake
Trying
shop?
to cut down
It's
my sugar.
Coffee. Yeah.
Yeah.
I mean, every now and again.
They opened up a new one in
I
Austin.
made waffles. this
Oh, really?
morning.
Yeah.
That is my, I know.
Nice.
Blueberry
Donut
waffles.
place.
Oh, sorry, what? I was
What?
zoned
No, I'm
out.
just listening.
No.
Thinking
No.
about donuts. Okay.
I was thinking about the waffles I made this morning.
Oh, nice, nice.
I got a story about the best cake shop a friend of mine ever went to, but it doesn't have a happy ending.
And then so C on this
Alright,
one.
alright, let's just put this
I'll tell you
Moving
later.
right
So anyway,
That's an after class
That's an after class class.
conversation. Yeah.
We're working on
Yeah,
3.5 for
the first one. If you go to the video, the last class I did most of the other problems.
Okay.
So feel free to watch that, and you'll get most of
It
the
helps.
answers basically.
Thank you, Keegan.
But I can do whatever now. But anyway, so this one has so what
I'll just follow.
the force is applied right at the point where we're measuring the torque around, right? And so what's the torque around the center? Sorry, around this point here.
Point if it's at the point.
It would just be 0. Yes. Those ones there's not.
Oh,
So-
okay.
So the torque around the point wouldn't apply because R is equal to 0 in this case.
Yes.
But it would still be rolling to the left, right? Same as in case A?
I don't know if it would be rolling if there were no friction.
Okay.
What would actually happen? Well, it looks like
It'd get pulled to the right if there were no friction. So that's the direction force is going in.
yes. If there were no friction, it would be pulled to the right.
But in this case, if it's being pulled and there is some friction to it, that means that it'll start rolling towards the
It'll
left.
move to the right and
Okay.
roll in the whatever way it has to move to the right. Yeah,
So for
a little bit.
that
But-
one, though, it's like no angular acceleration, no torque. It's
It
just
will not-
zero.
It
If-
won't move.
It's just it's not
Yes,
moving.
yes. There'll definitely be no angular acceleration around this point. Yes.
And then torque. There's no torque either. Just making sure.
Yeah. There's no
I
torque.
don't
Yes,
see
exactly.
why I
Yeah.
got that wrong.
Yeah, because they're
Okay.
parallel. But also the friction, even if there was friction, it's applied at this point too. So around that point, there's certainly no torque. But there's also the only other force there is gravity, which I guess is at the center, right?
Yeah.
And this is parallel to the R direction. It's anti-parallel, whatever, but therefore the cross product is 0. And so there's literally no possible torque at all around that bottom point. There might be torque, but in fact there is torque around the center. And we can find what direction it is by using this as R, and that's T, right? And now we take I would do break it into components. So we have one component like T going like that, and one component going like that, right? This is TX, TY. And now the vertical component that's parallel to R this isn't gonna affect it because it's parallel.
Mhm.
This is gonna affect it, so we have R across T is out of the board.
Yeah.
R cross F.
Got it.
And out of the board is this way, and so it's gonna rotate this way.
Okay.
And if it rotates this way, it's gonna roll actually that way.
Yeah, so it is going to roll to the left.
Yeah, okay, you're
Okay.
right then. Yeah. Look at that.
Wonderful.
All right. Did you so when it's the homework said 3.5, it said it
Yes.
twice. So is he talking
means-
about 3.5 and number
Yes.
5 the
Yeah.
police?
Yeah.
Okay. I was hoping
that
I'd be
took me a
wrong.
minute too.
Yeah, I was hoping I'd be wrong on that one.
The pulley one and some other pulley ones.
And then
And the last one
impossible
we just
rod
did today.
one.
Yeah.
Okay, so
Whatever
everything's
number
been
11
covered
is.
by the
I believe it's
Yeah,
all
you-
in
you
the last
did.
video, and then there's a video today that
Very
I'll
well.
put up.
That works out.
Maybe by tonight. It
You-
takes like a couple hours to upload, so.
You did that one very well.
Which one?
Thank you.
Police. This one.
Oh yeah, yeah. I was
So-
watching that this morning.
I got a few more questions about the chapter material then,
Yeah.
unless someone
Oh, good.
has some questions about the project or the homework.
No, take it away.
All yours.
Yes, that would be excellent.
Okay, so you all right?
It's great.
Cut the shit.
So
Yes.
okay, so let's see. Going here to figure 3.3. Okay. So it says okay, so as illustrated in section 3.3, when the angle changes by a small d theta right here,
Yeah.
the change in velocity is directed towards the center of the circle, but there's no indication that anything's directed towards the inside of anything.
This dv here is going down because if you're moving along a circle, right, and then you have some velocity here, and some velocity a little later is here.
Oh, I see. So the change
This
in
is going
velocity.
down. I mean, I drew it wrong. It's going straight toward the center. It's parallel to this. So the acceleration vector is always inward toward the center. That's what the centripetal acceleration.
All right. So my next part is for section 3.2.
Mhm.
So it defines the moment of inertia by as this.
Yeah.
Except I was wondering if there was like a straightforward one-step math proof that like showed how these two are related. Like I can't figure out for the life of me how the moment of inertia would require an integral of r squared.
Well, this is a torque.
Mhm.
No, sorry, it's not a torque, but it's it's not anything. Sorry. Yeah, I don't know.
Okay.
I mean, I do, but I can't
I-
think of a good way to.
You know, but okay, I know what you mean.
Like,
Okay, so maybe we could try it. Maybe I could ask it a different way then.
Mhm.
So, the moment of inertia, right, is essentially it's like we were talking about earlier. It's the combination of distance and force, right?
sorry, the moment of
inertia is a combination of distance and force, right?
does not have a force in it. It's a combination of mass and distance.
Okay.
Yeah. So
Let's see.
yeah.
All right. So
I mean, I can think of one thing to say about it, which is that force times r, or whatever, this is supposed to be torque, and force is supposed to be ma, which is m alpha r, right? This a is alpha r for this is a disk rotating. I'm being very schematic here, but and so so torque is really m alpha r times this r, right? And if we want to write it as something times alpha, it's mr squared.
okay.
That's the only thing I was thinking about. It's
Okay.
not a very good proof. I mean, really what it is that this is true. This statement is true for every piece of mass.
Okay.
And if you have something that extends now a disk has what we used is that A equals alpha r, but r varied for different parts of a disk. For here, r is a different value than here. So we actually have to do this thing, but for an integral over all where the pieces of mass are, right? there was no mass here, we don't have to do an integral or anything. But
Oh, I see. So the reason we need to do an integral is because the moment of inertia varies for every piece of mass in the system that we're looking at.
yes,
Okay.
yes.
So
In other words, this relation is sort of only equal for a one single piece of mass at some fixed radius. If we want to do it for an entire object with different radiuses,
Mhm.
then we have to do it. We have to actually add it up for each piece of mass, which is called this. But of course, if we have an extended object, it's called. This is the same thing. It's an integral.
So what would you say is the difference between torque and the moment of inertia?
That, like
Okay.
torque, like it's the same as the difference between inertia and force.
Okay.
Like they're sort of not the same thing. Like an inertia is a resistance to how forces act on objects.
Okay.
So if objects don't respond very much to forces, that means they have a very high mass, very high inertia.
So
Right. A moment inertia means if you apply a very strong torque, how does it accelerate? And how does it spin? If it doesn't spin that much, it must have had a really high something. That's called moment of inertia, because it doesn't necessarily have to have a really high mass. If it does, that's fine. But it also matters if the mass is near the outside. You know, if you have to spin like a hoop that's really heavy, versus spin a disc that's the same weight, it's actually easier to spin the disc. It's actually twice as easy, in fact, to spin the disc because a lot of the mass only needs to go this fast, whereas a hoop, all of it needs to go this fast.
Oh, I see. So it's like if we have a plank of wood, right?
Mhm.
And we decide to go ahead and rotate it from the very far end of one side or the
Yeah.
very middle of it.
Yes.
The moment of inertia is going to vary.
Exactly.
Okay, so the moment of inertia is a measure of how difficult it is to get something to rotate.
Yes.
All right. To
Exactly.
rotate, not to move, right? To rotate.
To exchange its rotation velocity,
Okay.
if you want to be really precise, 'cause
Okay.
it's acceleration. But yeah,
So
or
torque
to stop
then-
it from rotating.
So torque then is that something we could use as an umbrella term to talk about spin or a certain type of spin?
Torque.
Yeah.
Torque is a
If you
force applied on an object relative to another point. I suppose you'd say.
Okay, but isn't you mean like in a
Torque
circular motion though, right? Like the angle has to change? Because
Nothing
otherwise-
has to be changing. It's just that if you're talking about the force applied at a point that's different than another point, that always applies a torque around all the other points.
Okay, I think I
So
get it.
the torque doesn't necessarily have anything to do with rotation by itself. Just like force doesn't necessarily have anything to do with motion. You could have balanced forces and then nothing would be moving, or
Okay.
nothing would be accelerating.
So torque is the measure of applying one force over a certain distance to an object.
Yes, a certain distance away. Yeah.
Okay.
Yes,
you
that's
guys
good,
Have,
yeah.
You guys have any questions so far? All right. You guys want to take over? Just say the word, okay?
I mean, there's like 5 minutes left.
Yeah, 5 minutes.
Okay. You want to start a game show,
Yeah.
Keegan?
You're
All right. Finish the donut. You're gonna need your energy.
No, that's okay.
All right, so, okay, so I can understand that for an integral then, you're going to need it in order to discuss how all of the parts of a system are changing their
Mhm.
momentum or their acceleration velocity because of the change in direction. Okay, how do you explain the second derivative or the third derivatives like we're seeing in some cases, like these guys or these guys?
That just means this has more than one dimension.
Okay, so,
So-
if it's one dimension, it's one integral, two dimensions, two integrals, three dimensions, three integrals. Is that it?
Yeah, that's correct. But basically, this is true. This is the integral of all the mass of an object is equal to the total mass of the object. So I took out the r squared. This is just a separate thing. This is not the moment of inertia. This is just the mass of an object.
The integral of the mass of an object is...
Well, sorry, the integral of all the little pieces of mass, right? So if you had a rod,
Oh, because an integral is encompassing everything in a system to a certain point, right? So, like, you take an integral of the area under a graph. You're basically taking.
yeah. So if this rod, if you graphed its mass over, its distance, length, I guess, then and you had it would be constant.
Okay.
I mean, this is really the. This isn't how I want to say it. It's it's density. Okay. If I find it has a constant density over its entire length, then that means that dm is actually this little. I already drew it, but whatever. dm is this little piece of mass,
Mhm.
right? And dm, it turns out, is just rho times dl, because dl is a little piece of length.
Mhm.
And the little piece of length is related to a little piece of, another way of saying that is, right? This is the derivative of mass with respect to length, meaning if I take a small, like if I take a chunk of length that has some mass, and I keep reducing it and reducing it and reducing it, hopefully there's a thing that stays constant, which is the density.
Hopefully.
Yeah, I mean, because in other words, the total mass of the total length is the density, right? And if both of these are uniform, the length, of course, is uniform, but the mass is uniform the whole way, then this is true. So I can convert between dm and dl, and that way I get this integral of dm is rho times dl from the endpoints, because of course, technically it's an integral over all the space, but there's no mass here and no mass here. So it goes from 0 to L, and I get rho is a constant, so it comes out of the integral. Integral of dl is just L minus 0, which is rho L, and now I know rho L is the mass of the object, which of course is true if it has, I mean, it's sort of obvious here, but if I didn't know the mass, if I just knew the density and the length, then of course I could multiply them to get the mass. If it's uniform, it's just this.
Okay.
So, and if it has 2 dimensions, right, then I would need device like this, and it's, let's say, uniform, and now I have some, rho is like a surface density, so it's a density per little tiny square. That would be, I would have to do, let's say I had a length 0 to L and 0 to, I'll call it L2, it's a square. So it'd be 2 integrals where of the surface density, where I integrate over dx and dy. And now, of course, I just get L squared rho, which is, that makes sense if the surface density is, the mass over the area, right, which is, if it's a square, it's just L squared. So this is the same thing as that. And then you could do a third integral if you had a cube, let's say. You could integrate over x, y, and z, and you'd get L cubed for cube. Now, of course, this is not true in a round thing, because not a round thing, but like a disk, because it's really hard to integrate. Like, what are the limits of x if you have like a circle? Well, like, it starts here, but it doesn't. Like, it's really complicated. You could do it; it would be like square root of x squared plus y squared for a circle. But it might be easier to do it where if you integrate over the radius, right? So you integrate over dr, so one of the things is the radius, and the other thing is d theta, dr. So now, in other words, instead of adding up little squares or little, this is what we did here, we added up little squares with size dx times dy. Here we can add up little squares, but they have size dr times, now this piece here doesn't have size d theta, it actually has size r d theta, because like if we double the radius, we actually double the, right, the length of this arc here, the arc length is its angle d theta times the radius, right, that's the arc length formula. So if we take a small sweep of an angle d theta, the top dimension here is r d theta and the vertical is dr. So it's slightly different than this, where little tiny squares we can always say are dx dy. There's no special thing we have to do, or dy, x, dy, dz. In this case, we have to be careful because d theta is not actually a length of anything. D theta is an angle. The length of the square, is r d theta, and the width of the square, I guess, is dr. So we actually have to do this. And now if we, let's say, again, we have a constant density, we would get, we have to do 2 integrals. The r integral is going to go from 0 to the total radius, and the theta integral, of course, is going to go 0 to 2 pi. So it's very important that we know, it's not like this is obviously made it easy, but in this case, it's like this, and we get, the integral over theta, nothing depends on theta. This is just going to be 2 pi. The integral over, now rho also comes out. The integral over r is going to be r squared over 2, and we get rho times pi r squared. This is the area of a circle, obviously. So this is the same as if you had a mass of a circle that has, the density of a circle is mass over the area, where the area is pi r squared. Sorry, this would be capital R. Anyway, and then we could do it again for a sphere. I'm not going to do it because it's hard, but it's the same thing, but now we have to take a little cube kind of thing of a sphere, but now we have to worry about that there's 3 angles. It gets a little harder. And we have a different, it's called this number here, this r, the fact that it's not just dr d theta, it's actually r dr d theta. that number is called the Jacobian. If you've ever heard of that before. So if you've ever heard of a Jacobian, that's this r here. If we want to do a three-dimensional integral for a sphere in spherical coordinates, we could. It's just r squared sine theta dr d theta d phi, where phi is the this is spherical coordinates where r is the distance from the center again. Theta is the angle from the North Pole. So it's the latitude, right, kind of thing. So the North Pole has theta equals 0, the South Pole has theta equals 90, and the equator has theta equals 0. So that's theta. And then phi goes around. So you have it's like the, time zone kind of thing, right? It goes around the sphere. So that's this, and of course, if you want to take a little chunk somewhere, it would look like a little cube, but if you wanted to actually find the dimensions, it would be something like this. So this here is called the Jacobian because it's sort of, you don't expect it. You expect just the coordinates here, but the Jacobian for x, y, z and stuff is always just 1. It doesn't have 1, but anyway, so that's, well, why were we talking about this? Oh, that's how you, well,
three integrals.
that's how you go, so it's always dm r squared. That's always I, right? But dm could be decomposed into, the mass could be distributed over 3 dimensions, let's say. Then you would convert dm into, it's not a conversion, it's just they're equal. It would be equal to, maybe something times dx, dy, dz, maybe. I'll call this density rho or whatever, right? And now, of course, that would be actually how you'd solve it if you wanted to solve these. So they write that as the formula. I don't know how many times you'll need to actually solve it, but that would be how you'd solve it, is you'd have to break it into coordinates, explicit coordinates, because you need to integrate over. Mass is not a coordinate, right? It's just a number. It's like a mass, right? You actually need to explicitly break it into coordinates and then because you have 3 d's here, you need to do 3 integrals, and each integral corresponds to 1 of the dimensions. And if you break it into these 3 coordinates, it's still the same 3 dimensions. It's just that you need to be a little careful because there's an extra term here. But okay, I'm happy. All right. All right. So this will be online, and hopefully this.